So, as most of the people have said that we want explanation once again, so I will do the derivation part once again. So, we have started from here. See here, this is a second order system, and the second order system transfer function is equal to x of s divided by f of s is equal to, also called as output divided by input, c of s upon r of s is k divided by ms square plus bs plus k. I have taken, I will see that there is no coefficient in front of s square. That means coefficient of s square should be 1. So I will multiply and divide it by m. So the equation becomes like this. I will substitute the values of k by m as omega n square and b by m as 2 zeta omega n. So the equation becomes like this. Omega n square divided by s square into 2 zeta omega n is into plus omega n square. So if you see the denominator, it is a second order equation. The s will have two roots. So the two roots are minus b, that is minus zeta omega n, plus or minus under root of b square, that is 4 zeta square omega n square, minus 4ac, that is 4 into a, that is 1, into c is omega n square, divided by 2a, that is 2. So after simplification, it will become like minus zeta omega n plus or minus omega n into root of zeta square minus 1. This is possible only if the zeta, that is damping ratio, is greater than 1. Then if the zeta is less than 1, that is under root quantity becomes negative. So root of minus 1, I am taking it out. So indirectly I am taking negative sign common inside. So it becomes 1 minus zeta square instead of zeta square minus 1. And the roots will be these two. If zeta is equal to 1, either you substitute here or here, no difference. If you put zeta is equal to 1, this under root quantity becomes 0. So this will vanish. Zeta is 1. So both the roots are minus omega n only. So when zeta is greater than 1, it is overdamped, equal to 1, critically damped, and less than 1, it is underdamped. Underdamped system is most important. Now, as there are three types of second order systems, that is underdamped, critically damped, and overdamped, you have to do each derivation 3 times. Step input derivation 3 times, ramp input derivation 3 times, and impulse input derivation 3 times. Totally 9 derivations are there, which cannot be covered in the class. That is what I said. But to start with, when zeta is less than 1 and we are substituting step input, that is 1 upon s, unit step input. So if I put r of s is equal to 1 upon s, so c of s becomes, that is omega n square divided by this s will come because of this. Now this under root part, this bracket part, as we have seen in the previous class, previous slide, has two roots, s1 and s2. Here I am putting root of omega n into root of 1 minus zeta square as omega t, so that repeatedly writing down becomes easier. So this is called as damped frequency of vibration for underdamped system. For overdamped system, the damped frequency of vibration is omega n into root of zeta square minus 1 for overdamped. For underdamped, it is 1 minus zeta square. So here if you see that the denominator has 3 brackets. One s is there, s plus s1 is there, s plus s2 is there. So if you simplify it directly like this, or by using partial fractions like the first order system. So like a first order system, This can be written as A upon S, B upon S minus S1, B star upon S minus S2. So this minus of minus sign becomes plus. So if you evaluate A, B and B star by usual method, how to evaluate A? Multiply both sides of the equation by denominator of A, that is S, and then take S tending to 0 and evaluate A. A will be 1. Similarly, if you evaluate B, to evaluate B, you have to multiply both sides of the equation by denominator of B, equate denominator of B tending to 0, get B, and B star will be same as B only because it is complex conjugate. Only thing, positive sign becomes negative sign. If you simplify it further, then you will get here that C of t becomes equal to this equation. That is 1 minus e to the power minus zeta omega n into t divided by root of 1 minus zeta square into sine phi cos omega d into t plus cos phi into sine omega d into t, where what is cos phi? It is zeta. What is sine phi? It is root of 1 minus zeta square. And tan phi is root of 1 minus zeta square divided by zeta. It is explained by the triangle. So this is theta, this is x, horizontal line is zeta, vertical line is root of 1 minus zeta square. This is 1. Then substituting back into this equation, cos a sin a cos b cos a sin b can be written as sin a plus b, that is sin omega d into t plus phi, where omega d is once again explained here. It is root of 1 minus zeta square into omega n. Is it clear now? Yes? Is it clear? Yes, sir. So coming back to the next step, here the complete, this is another way of doing the same derivation alternately. See here, this is explained like this. Here it is simplified as this much, and it is written like this. This is another way of doing, instead of doing the partial fractions, this is another method. You go through that. Finally, you will get the same answer. You will get the same answer. So, step input response. This is the derivation which I have done. For different values of zeta and omega n, we have plotted the graph. Looking at this graph, if the input is 1, R of S is 1, or R of T is 1, R of S is 1 upon S, you will get output like this. That means if you see this, output will overshoot the input. It will instantly become more than 1. It depends on the value of zeta. As the value of zeta goes on increasing, this overshoot goes on decreasing. And then finally it will stabilize. When it will stabilize? When t is infinity. See, if the C of t has to become 1, that means this under root part has to become 0. When this under root part will become 0, there is one cos function and sine function is there. Cos and sine function cannot become simultaneously 0. That is out of question. When the cos becomes 0, sine is maximum. When sine becomes 0, cos is maximum. So this cannot become 0 at any given instance. Only this part has to become 0. anything to the power minus infinity is 0. So e to the power minus, when t becomes equal to infinity, because zeta and omega n cannot, they are system specific. They cannot be infinity. Only t can be infinity. When the t can be infinity, when the t is infinity, this is infinity, the minus infinity. So e to the power minus infinity is 0. 0 multiplied by anything is 0. So it will become 1 only when t is infinity. So these oscillations for underdamped system will die down when time t is infinity, which never comes. That means these oscillations keep on continuing for permanently, or they become so small they can be neglected. So if the zeta value is now increased, these oscillations have come down. See here. And even the overshoot also has gone down. In the previous case, it has gone up to 1.7. Now it has gone up to 1.2 only, approximately. And these oscillations are lesser. If the zeta further increased, 0.9, oscillations more or less has died down. So here if you see that as the zeta goes on increasing for same frequency, natural frequency, then the output, there is no oscillations or reduced oscillations. In the second case, for critically damped condition, then zeta is 1. When zeta is 1, both the roots are equal minus omega n. So S plus omega n into S plus omega n, two terms will be there. So that means S plus omega n whole square. So once again, I am subjecting it to step input 1 upon S. So once again, A, B, C, these three partial fractions you have to evaluate. So evaluate A, multiply both sides by denominator of A, that is S, and take S tending to 0. So you will get A as 1. Then similarly, B as minus 1 and C as minus omega n. How to get that? This means there are two terms here. Why B and C? Even these two terms in the, if you remember in the previous class, we have done complete derivation of ramp input. In the ramp input, square term is there. A square term is there. For that, what we have written 1 upon S and 1 upon S square, or B upon S, C upon S square we have taken. Similarly, here also I will take B upon S plus omega n and C upon S plus omega n square. So first you evaluate C. Once you evaluate C, then differentiate and evaluate B. So here these partial fractions are written like this. 1 upon S minus 1 upon S plus omega n minus omega n upon S plus omega n square. Then you take the inverse Laplace. 1 upon S becomes 1. 1 upon S plus omega n becomes e to the power minus zeta omega n into t. And omega n into this becomes minus omega n into t into e to the power minus zeta omega n into t. These are standard inverse Laplaces. So it is simplified like this. Once it is simplified, if you plot the, for the overdamped case, when the overdamped case, the two roots are S1 and S2 minus zeta omega n into root of, there are no complex conjugate parts here. So there is no complex variable because under root part is positive. So the two roots are different, one with plus sign, one with minus sign. Once again, this is written like this. Then take the three partial fractions like this. Evaluate A, B, C. A is, generally A will be 1 only. B is this much. Then C will be a complex conjugate of that, will be this much. Then you put these three and take the inverse Laplace and simplify. The output equation becomes like this. This is the third derivation for step input. Similarly, you will have three derivations for ramp input and three derivation for impulse input, that we are not going to do it. So if you go through the book, There the partly the derivations are done, but you will come to know the final equations there. In all the books it is available. Then here all the three cases are put in one graph. Under damped, there are oscillations. When zeta is 0, it goes on oscillating forever with the same height. Then as zeta goes on increasing, these oscillations die down faster. When the zeta becomes equal to 1, it is more or less like a first order system. And if the zeta further increased, 2, 3, 4, 5, 6, this is sluggish response. Slowly it will reach equal to input or 1, and it will never overshoot. It will overshoot only in the case of underdamped system. That is zeta less than 1. For critically damped and overdamped system, there is no overshooting. Is it clear? Now, first order underdamped system subjected to unit step input, we are going into further details of that. Only this particular system we are going into further detail, that is underdamped second order system subjected to unit step input, which is a very common case of your suspension system. A suspension system is either subjected to step inputs or it is subjected to impulse input. Never you come across ramp inputs. So here what happens is, for unit step input, the further details are plotted here. See here the output graph. This is input is 1, output overshoots and oscillations continue. These oscillations can continue for infinite amount of time, but you cannot wait up to infinite time. If you provide some tolerance band, and from that you can find out the parameters. The first parameter is rise time. It is time taken by the system response to reach equal to input, that is 1, in the first attempt. Second one is peak time. It is output time required for the system response to reach the peak of the value, highest value in the first attempt. And the third is settling time. It is time taken by the response to reach and stay within a tolerance band of either 2% or 5%. That is, it should keep on oscillating between 1.02 to 0.98, or 5% means 1.05 and 0.95. So here we'll start the derivation of rise time. I am taking the initial equation of second order underdamped system. This is second order underdamped system only. This is output equation which we have derived. That is, instead of cos and sine function, I have taken, that is cos sine A cos B, cos A sine B type of equation was there. That is, can be written as sine A plus B. This is in the form of sine A plus B type. Then what I will do is, this is a function sine A plus B type. I am substituting phi here as tan inverse of zeta, 1 minus zeta square divided by zeta. Then rise time means it is time taken by the system response to reach equal to input in the first attempt. So when it becomes equal to input at time t equal to tr, output should be 1. So I have put it here. So if you put it, output should be 1 means left hand side is 1. So 1 is equal to 1 minus something will come. So if it has to become 1, this minus part should become 0. This minus part is becoming 0. In this minus part, there are two things. E to the power something is there and sine function is there. So e to the power minus part cannot become 0. It can become only 0 when t is infinity. So in the first attempt, time is not infinity. So that is not the case. So this function has to be 0. That is, sine omega d into tr plus phi should be 0. Sine omega d into TR should be 0. Yes? Any questions? So that means sine theta can be 0 if theta is either pi, 2 pi, 3 pi, 4 pi, so on, or n pi in general. So that means, so output reaches equal to 1 number of times. If you see the graph, it will reach equal to input number of times. Here it has become 1, 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 so on. It keeps on becoming 1 number of times because it is oscillating. So when it becomes first time, that is what is a rise time. So when it is becomes the first time, I will put it as pi, not n pi. N is 1 first time. So if I put it equal to pi, then TR from this equation is equal to pi minus pi divided by omega d, or pi minus pi divided by omega n into root of 1 minus zeta square. I have put the value of omega d. Or in general, TR is equal to this much, where pi is, we have seen in the previous slide, pi is tan inverse of root of 1 minus zeta square divided by zeta. So here in the numerator, everything is in radians because pi is in radians, and tan inverse you have to take it in radians only. So the numerator will be in radians. In the denominator, this under root part is a constant, 1 minus zeta square, so don't have units. Whereas omega n is radians per second. So this radian and radian cancels. This second, which is in the denominator, comes to the numerator. So time will be in seconds. Remember, time will be in seconds only, provided you take tan inverse in terms of radians. Remember one thing, this is a common mistake done by most of the students in the exam. They keep habitually their calculator is in a degree position. If you take tan inverse in degrees, then the answer will go wrong. It has to be taken in radians only. So next derivation is peak time. Peak time is time taken to reach the peak of the response. How to find out the peak? Maximum value. Peak means maximum value. You differentiate that equation with respect to t and equate it to 0. I have differentiated this equation with respect to t, and this 1 becomes 0. Differentiation of 1 is becomes 0. This remaining part will have two parts. E to the power something is there and cos function is there. So if you take this and this separately, u by u and u into v method, and equate it to 0, then this equation becomes like this. When this equation becomes like this, and finally if you simplify that, it will become the equation for Tp will be that whole part should become 0. That means in general it is sine omega d into Tp should be equal to 0. Then omega d into Tp should be 0, pi, so and so. 0 cannot be the answer. So first time it is a peak value will take at pi, then it will happen at 2 pi, then it has 3 pi, so on. So but highest peak will happen at pi. So I equated to that. So Tp I have found out like this. So this is the derivation of Tp. So in general, you have how many derivations now? 9 derivations will be there for second order system. Step input 3 derivation, ramp input 3 derivation, impulse input 3 derivation. Then for underdamped systems, for step input, you have further specialized derivation. One is for rise time, second one is for peak time, and third one is for peak overshoot. When the peak overshoot you are considering, the peak overshoot means it is difference between the peak value and the mean value, that is 1. So peak overshoot is found out as peak value which will happen at CTP, and mean value is 1. So this minus this. So I have done like that. So this 1 vanishes, only minus part will remain because this minus 1, this 1 cancels. So this I am putting TP value. TP value we have calculated in this previous derivation, that is pi upon omega d. This pi upon omega d, I am putting it here and simplifying. Then it will become like this, e to the power minus pi into zeta divided by root of 1 minus zeta square. So it will be in a fraction. If you want it in percentage, multiply it by 100. So how much percentage it overshoots, that you will come to know. By how much value it comes to that also you will come to know, that is fraction value. Otherwise, by how much percentage, if you want, multiply it by that fraction by 100. Whereas for settling time, it is not setting time. Remember, it is settling time. Remember, this is a settling time. Settling time, there is no derivation. For 2% tolerance band, it is 4 divided by zeta omega n. For 5% tolerance band, for 5% tolerance band, it is 3 divided by zeta omega n, where zeta is the damping ratio, omega n is natural frequency of vibration. These are other 3 derivations, and another one, settling time, direct equation is there. There is no derivation for that. So here, this is our standard second order system. This sine phi is 1 minus zeta square. That is taken. Sine phi is 1 minus zeta square. That you remember. It is written somewhere. Okay. Now here the example is there. Determine undamped natural frequency and damping ratio of following second order system. Okay. This is our second order system given it to you. 4 divided by s square plus 2s plus 4. Okay. You try to compare that with your standard second order system. This is our standard second order system. Omega n square divided by s square plus 2 zeta omega n into s plus omega n square. Now, compare the two. See here, 4 is omega n square, but don't compare with this numerator. See, what happens is, why you don't have to compare with the numerator reason is, numerator may consist of some gains also k. That k value, if suppose if it is 2, instead of 4, it will be 8. Now k value is 1, that's why it is same. Otherwise, it is not necessary that this equation is this and this value should be same. It is not necessary. Here it may be 8 or 10 or 2 or 1, whatever it may be. So only compare the denominator part. Remember, you concentrate on the denominator part of the standard equation and given equation. This is our given problem. This is our standard equation. So from this you can see omega n square is 4. Is it okay? Omega n square is equal to 4. So omega n is 2. Omega n is 2. Similarly, if you compare these two, 2 zeta omega n is equal to 2. 2 zeta omega n is equal to 2. 2 zeta omega n is equal to 2. Okay. So zeta omega n will be equal to 1. Omega n value you already know, that is 2. So from that zeta you can find out as 0.5. So once you know omega n and once you know zeta value, you can find all other time response specifications. So these are called as time response specifications. What are time response specifications? Rise time, peak time, settling time, and peak overshoot. These are called as time response specifications. No, in the question paper, it is not necessary that they will specify find rise time, peak time, something like that. In single sentence, they write determine all time response specifications. To get the time response specifications, you need only two values. One is natural frequency of vibration, omega n, and damping ratio. and that damping ratio should be less than 1. Otherwise, it is not possible. So this is what is the simple problem. So after knowing this, you can proceed further. Now you know zeta value, you know that is 0.5, and you know omega n value, that is 2. So you go on substituting these values in rise time, peak overshoot equation. See here, we can go back. Here you can see rise time. This is a rise time equation. First, we can see the rise time equation. What is rise time? TR is pi minus pi divided by omega n into root of 1 minus zeta square. Now put pi is known, minus pi. What is pi? Tan inverse of 1 minus zeta square divided by zeta. You know value of zeta? 1 minus zeta square divided by zeta, you do take under root and take tan inverse in terms of radians and subtract from pi, and here omega n value is 2, zeta value is 0.5, substitute, you will get a rise time. Similarly, you will get a peak time derivation we have seen, and peak time is equal to pi divided by omega n into 1 minus zeta square. So pi is in radians, zeta omega n is radians per second. So that second goes to the numerator. You will get the value of TP provided you know omega n and zeta, which is known. Omega n is 2, zeta is 0.5. So zeta is 0.5 means 0.5 square means 0.25. 1.1 minus 0.25 is 0.75. Root of 0.75 multiplied by 2 pi divided by that. Pi is 3.14. So you will get TP value. Similarly, you can find out MP value. This is the MP equation. Put zeta value. Omega n is not at all there. Only zeta value is sufficient to find out the peak overshoot. So multiply it by 100 to get it into percentage. Then settling time, these are the two equations. You know zeta, you know omega n. Zeta is 0.5, omega n is 2. So your denominator becomes 0.5 into 2 is 1. So settling time 4 seconds or 3 seconds. 3 seconds for 2%, 5% tolerance band. For 2% tolerance band, it is 4 seconds. This is the time response specification. So this type of problems only you will get it. See what in the problem, what you have to do is the problem is given in a such a way, from that you have to find out value of zeta and omega n. Once you do that, other time response specifications can be simplified. So remaining problems, one or problem, only derivations are very complex here. Problems are very simple. So that's why you can expect one derivation at least in the exam. Problems are very simple, and problems will be never more than 5 marks or 10 marks, not more than that, because the problems are very simple. So tomorrow's class will see some simple problems just like what we have done today, and we'll finish off this chapter. So the unit number 2 is complete in all respect. So after that I will start the unit number 3 and we'll finish that. So here I will take the break for today. Do you have any questions now? Have you understood now? Same thing I have repeated fully. Have you understood that?
Yes, sir.
Okay.